Good afternoon, everybody. My name is Fiona Doyle. I'm the Executive Associate Dean in the College of Engineering, and I'm also a Professor in Material Science and Engineering. So it's a great pleasure for me to welcome you all to this Dow lecture on behalf of the College of Engineering. I'd also like to take this opportunity to express great thanks to the Material Science and Engineering Student Association, MSEA, for their assistance in organizing this event. For large college events of this nature, we ask student groups to co-sponsor them. So I'm thrilled that MSEA has been involved in this one, and as with all of our student groups, has been invaluable. The Dow lecture has been in existence for a few years now, and we are incredibly grateful to Dow for providing the funding to allow us to bring annually to the campus a true luminary in the field of material science and engineering. And we've had some very distinguished speakers. I must say that I am truly thrilled and honoured that John Cahn accepted our invitation to give this year's Dow lecture. So without further ado, I'm going to turn things over to Mark Astor, the Chair of Material Science and Engineering, who will introduce this year's Dow lecture.
Okay, good afternoon. Welcome to this year's Dow lecture for Material Science and Engineering. And it's really a great thrill for me to be able to introduce the speaker. In many ways, the speaker needs no introduction. John Cahn is somebody whose work has touched so many aspects of material science and engineering and had so much impact on our field that I think all of us probably remember, when we read our first John Cahn paper and how it influenced our work. So what I will do is I want to keep this kind of brief because John has, I think, a really interesting talk to give us, and I want to make sure he has enough time. But I did want to mention a little bit of his background. For those of you who don't know, John's actually an alumnus of the University of California, Berkeley. He got his PhD in chemistry in 1953 from UC Berkeley. And in 1954, he joined the chemical metallurgy research effort at General Electric Laboratory. So he left and went to industry right after his PhD. And then in 1964, he became a professor of metallurgy at the Massachusetts Institute of Technology at MIT. And he was there until 1978 when he joined at what was at that time the National Bureau of Standards, and now we know it today as NIST, the National Institute of Standards and Technology. And he retired in 2007 and remains extremely active now as an affiliation at University of Washington, where he has appointments both in physics and material science. John is his contributions to the field, as I mentioned, are really extensive. He's made pioneering and really important contributions to the theory of phase transformations of materials. The theory of spinol decomposition is something that many of us in the audience are no doubt familiar with. But he's also made enormous contributions to solidification theory, to wetting theory, and to the glass transition. And also, as many of you may know, he was the co-author on the paper on quasi-crystals that really introduced this topic to the field, and that, as many of you know, the quasi-crystals received the Nobel Prize in Chemistry last year, and I think John is actually going to mention quasi-crystals in his talk, so we'll hear more about that. So I'll just end by noting that John has a very extensive number of awards and honors. If you go to his Wikipedia page, you come up with a list of about 50 awards and honors, and so I clearly don't want to go through all of them, but some of them are really extremely impressive, and so I want to mention that he was voted to the National Academy of Sciences in 1973, and then the National Academy of Engineering in 1998, and many of you know to be a member of both of these academies is really quite something extraordinary. In 1998, his work was recognized with the National Medal of Science, and in 2011, he received the Kyoto Prize for advanced technology. For those of you not familiar with the Kyoto Prize, it's basically described as the equivalent in Japan of the Nobel Prize. So this is a very, very big honor. And so John, I don't want to take up any more of your time. So without further ado, let me turn it over to John Cahn, and please welcome.
Well, it's indeed a great pleasure to be here. I was on this campus 60 years ago, and I took the course from Professor Hultgren. I was a chemist doing reaction kinetics in aqueous systems. I had a thermostat at 20 degrees centigrade, and I never had to cool it. The lab never got up above 18 degrees centigrade, and I don't know what's happened to the climate. Is there a climate change? Anyway, Professor Hultgren convinced me that there were fascinating problems in metallurgy, and Professor Asta did not mention that I had 2 years at Chicago at the Institute for the Study of Metals before going to GE, so there was a 2-year period where I was with Cyril Stanley Smith's group, and then went to GE and then to MIT and so on. I've been fascinated by the changes in this building and the changes in the kind of research that was done. 60 years ago, we tried to simplify things as much as possible in order to isolate phenomena and to try to understand them. Today, we are doing much more construction of complex systems because we understand each of the individual components of it. So we can make multi-layers, we can go to complicated alloys, and that was not my style. My style was always to keep simplifying until I finally understood what it was that was bothering me. So anyway, this is a thing where I took Professor Hultgren's course, and this class in 51 had several chemistry graduates as well as some graduate students from metallurgy, and we had intense discussions. And instead of just listening to Professor Hultgren, we kept asking for deeper and deeper things, and we discovered there wasn't any deeper thought. And so anyway, I had this idea that this would be a good career starting point. And what I want you to get from this lecture is that there continue to be really important unanswered questions, and I'll go through some of the ones that I've answered and some of ones which still puzzle me. But if you have 61-year careers, you will see enormous changes, and everything you've learned here will be obsolete long before the 61 years are up, and there'll be an entirely different kind of knowledge and field. So what the professors are going to teach you now is almost certainly fallacious. There will be fallacious things in it. I've taught fallacious things. As poor students, they have to learn as they are taught. That has to be useful for answering the quizzes. You have to give the fallacy even though you think it's a fallacy. But keep track of them, because one of these days you may discover that you can do something about it. Now, I'm talking, making plausible explanation is part of human nature. And in a field like ours, there are so many phenomena, and plausible explanations simplify what is known. They rationalize correlations. They create rules of thumb that we use to solve problems. They make predictions. They advance the science and technology. And they may infer what will eventually become a scientific law. And it's still true. But they may be wrong. They are temporary, they may be wrong, some of them may become laws even though they're wrong. But when should we take notice and what might be the payoff? So I'm going to go in 60-year intervals. 51 is when I learned about metallurgy till now. 1891 is 60 years, and pre-81. Fallacies persist because they're plausible, because they're judged useful. Sometimes they're poor definitions. They continue to be taught, and there's nothing to replace them. Replacing of a plausible fallacy may be a paradigm shift, and that is the inconvenient truth, because they require mid-career learning. The professors have to change what they teach. The people who are out working may have to learn what they did, something that they didn't, maybe too difficult. And so these are the inconvenient truths. They come part and parcel with getting rid of plausible fallacies. Now here's something from my friend Ed Hart. Here is a principle, and it predicts this. Here's the experiments show up this way. Wonderful, there is agreement here. Now, let's find a plausible explanation for the deviation. And so, but there are many things that are kept because once it worked, for that point, it worked. So let's go way, way back, and I mean just to the years of alchemy. Scheele, in the mid-1700s, had this idea, and he was an alchemist, that metals are phlogistinated calxes. Now, charcoal had a lot of phlogiston in it, and calxes, which he considered to be the basic elements, were the oxide, the minerals, the carbonates. And he just decided to heat an awful lot of them, and he also, by the way, hydrogen was also pure, almost pure phlogiston, and that led to the discovery of several metallic elements. So he discovered these elements by just following that rule. Now, this was a very useful rule, and the only thing that was trouble with it is that the calxes were not the basic elements. We now know them to be oxides, and that phlogiston removes oxygen, so everything was a little negative. At the same time, Benjamin Franklin, when he went into electricity, he saddled us with the fact that it's a negative electron that conducts the electricity. So we always have to worry about signs and everything, but we've kept Franklin's definition of negativity. The one that is one of my favorites is that steel is iron purified, ennobled. Steel is something noble, iron is something ordinary, and it is ennobled by fire, and it's a charcoal fire, and this worked for millennia, and there were lots of craft knowledge for it. If you left it in the fire too long, it became burnt. That was brittle. It was too much carbon, as we now know. The fire, they said the fire draws the bad sulfurous elements through pores. That's vacancy diffusion. Today, much of our diffusion occurs by pores moving through the metal, but these guys didn't have the luck of inventing that. And it was a batch process. It was not homogeneous because the bloom that came out was highly carburized on the outside. That made one kind of steel, and the interior didn't have much carbon in it, so they had to separate it. There was a guy in 70s, Bergman. He was playing around with acids, and he had a calorimeter, and he dissolved various irons and steels. And what was the iron adding? It was adding phlogiston, which had turned it from a calx to an iron, but also caloric. So he was thinking it would store heat. But when he dissolved steel that had been in the fire for much longer than the iron, it gave the same heat. So it didn't store caloric. But the other thing that was found is that for the steel, there was a carbon residue. Whereas when the iron dissolved, there was no residue. And so all of a sudden, there was the idea that steel is an alloy of iron and carbon. And this was an enormous revolution, because instead of batch processes, you now had huge batches. Instead of small plumes, you had huge batches. And you controlled the carbon content, which you could analyze. And the steel industry of the 19th century was the result of this guy doing his things. Now, another fallacy, which will come back later, is that throughout the 19th century, all crystals are composed of three-dimensional packings of identical units. It came from Abe Aoi in the 1820s. And mathematics put this on a wonderful thing. They found out exactly 32 point groups, 230 space groups, everything rational. There were catalogs. But the other thing about that is if crystals are composed of small units that packed in identical units, you wind up with definite proportions. Every one of those units has so many atoms of this and so many atoms of that, so it's definite proportion. And definite proportion was still the idea when I was a student in chemistry. I mean, we talked about sodium chloride crystals as being composed of sodium chloride molecules, and so on. And the things that were not definite proportions, they were queer. There was something wrong with iron oxide where it wasn't exactly 50-50. So solids were stoichiometric. They had definite proportions, and those proportions were rational. So that comes all the way back from the 1820s. Now, 1891 is as far from the time that I was a student as 1951 is for you. So this is, to me, that seems terribly ancient. And I want to just talk about the fallacy. All crystals are three-dimensional, obey the laws of definite proportions. Indefinite proportions are sum honors. Solids are inert. I mean, would you expect atoms to move about in a solid? A solid is solid. So there is no diffusion. And the only way you could react a solid was to vaporize it or dissolve it. So that was the firm belief then. So diffusion is not possible in solid. Now, these three things make precipitation hardening impossible, because in a precipitation hardening, you have variable composition. You heat a metal until it dissolves. You heat an alloy until everything is in single phase. Then you cool down and you let it go into two-phase and get precipitates. So diffusion, indefinite proportions, none of those were true. So between 1891 and 1990, all of those had to be killed. And so one of the amazing things that is true throughout this story, and I didn't emphasize it before, is that there were two communities. There were the people at the universities, the philosophers, the natural scientists, the physicists, the chemists, and so on, and then there were the craftsmen. And we in our field date precipitation hardening to Wilm's discovery in 1909 of duralumin. This was an alloy that he was testing the hardness of. Aluminum was useless. It was much too soft. It couldn't be used for anything. And he made a test of its hardness on Saturday just before going home for the afternoon. In those days you worked 5.5 days. Came back on Monday and decided to test the hardness again, and this alloy had gotten harder over the weekend. And that became the big commercial alloy that was used for airplanes in the First World War and was around everywhere. But 6 years before, the Wright brothers specified that their aluminum engine be cast of 8% aluminum by weight. And we don't know what they specified in terms of heat treating because it doesn't age harden at room temperature. So they must have either specified a slow cool or they must have heated it to about 200 centigrade. And in 1904, there was an aluminum bicycle in the St. Louis World's Fair. We've been trying to get a hold of it. We don't know where it is, but the Wright engine has been tested, and indeed it has precipitation hardened. It has the Guinea-Preston zone of something that has been heat treated, and not aged at just room temperature. So the craftsmen, in this case the bicycle people, knew about a way of getting hard aluminum, the rest of the world didn't. By 1919, we knew about solid solutions. That came about 1915 by a big lecture. We knew about diffusion. That came in 1899, and I'll talk a little bit about that. And we knew about phase diagrams, that there was solid solubility and there was diffusion. So all of the things that went with it. And Merica et al. Said that duralumin is precipitation hardening at room temperature diffusion. We can do the same thing with other alloys by going to a temperature where the atoms still move. And that was an enormous shift. And within 10 years, every metal had been hardened in one way or another by precipitation. And it's a wonderful way of hardening material. And it also led to beautiful work on phase diagrams that now became important for development. And of course, in 1937, Guinea and Preston, with diffuse X-ray scattering, discovered that, and this is the beginning now of diffuse scattering as a way of testing things that are too small to be seen in a microscope. I just want to show you here how deeply impeded science was. Here is J. Willard Gibbs on volume 1, page 79, talking about solids. If any of the homogeneous masses of which the equilibrium is in question are solid, it will evidently be proper to treat the properties of their components as invariable. You can't change the composition in the application of the criterion of equilibrium, even in the case of compounds of variable proportions. So he's aware of the fact that some of them are not definite proportion. That is, even if bodies can exist which are composed in proportion infinitesimally varied from those of the solid considered. So these solids, which are absorbing fluids, form, of course, an exception so far as their fluid components are concerned. He's talking here about how do you vary composition, and he thought that these would be fluid components. I think of this as wet wood, but Lee Darkin and Oriani said, well, this is a wonderful example of carbon and steel. The carbon is the fluid that diffuses through the lattice, and the iron carries the load. It is true that a solid may be increased by the formation of a new solid matter on the surface, epitaxy, where it meets the fluid, which is not homogeneous. So if you make something epitaxial, which is not homogeneous with the previous existing solid, such a deposit will properly be treated as a distinct part of the system, as one of the parts which are new. He's not allowing even for an infinitesimal layer to diffuse with this. So he was simply stuck with being rigorous, but with his crazy ideas about solids. So anyway, the craftsmen knew that you could not gild lead. That if you put gilding on lead, it was gone within 6 months or so, so it must diffuse in. And Robert Austin in 1899 decided to make that into a diffusion couple, and he said, my God, there is solid-state diffusion. So now the scientists were on the same wavelength as the craftsmen. And so on. I want to emphasize Darkin, after the Kirkendall effect, finally says there are vacancies in metals. But he's very careful not to say it too strongly. The ionics in 1920, already you had Wagner and Schottky effects, but here were two fields which I consider to be both fields of my own, which in the 1920s and 30s were separate. Metallurgists didn't talk to ceramists. So it was a big shock to them to discover that there were vacancies. And then there's a lot of work with grain boundary, and I'll talk a little bit about that. Okay, fallacies in my time. The same thermodynamics can be used for liquids and solids. I did a lot of work with Larcher to show that the elastic effects of compositional inhomogeneities and so on can't be ignored, and certainly the elastic effect in spinodal decomposition can't be ignored. The free energy changes caused by a process drives it. Assuming surfaces and interfaces to be isotropic, until recently, practically nobody allowed a surface to be anything but isotropic, even though every microstructure that you saw had corners and facets and so on. Then something wonderful, I don't know which professor it was here at Berkeley who told me, atoms are a theoretical construct that will never be seen, and I should be prepared for the day when that'll all be overthrown and be taken over by something new. And another professor told me that the only use of semiconductors is that their existence confirms a prediction of quantum mechanics. So you had insulators which were useful, metals which were useful, and one theory connected them, and that predicted that there would be something like semiconductors, and that was sort of nice. So glasses are amorphous without structure. I'll talk a little bit about that. And of course, that thing about that still was very much part that all the crystals are of a packing of. Well, here's what happened. Dan Schechtman, working with us on our rapid solidification project, found five-fold symmetry. This is the original diffraction pattern. It looks like a tenfold, but note that a transparent polyhedron with a five-fold rotation axis will sometimes look like a tenfold axis, so that's what happens. When he rotates, he found that he had the five-fold pattern there. He rotated in one direction, big 5, 2, 5. He rotated in another direction, 5, 3, 2, 3. And here we have 5, 3, 2, 3, 5, to 5. This is a ball I got in Japan. Here is an icosahedron, 5 to 5, 5, 3 to 3, back to 5. And here is a quasi-crystal, same shape as this. So it really... So what are the laws? The laws are that a diffraction pattern of crystal has the same rotational symmetry as the crystal itself. And then there's a theorem, the crystallographic restriction. The rotational symmetry of a lattice can only be 2-fold, 3-fold, 4-fold, or 6-fold. Therefore, crystals with lattices are forbidden to have 1 5-fold axis, let alone 6 of them. Just to remind you, it's a very simple proof. I take a shortest distance from A to B, that's a D, and I take any angles less than 60 degrees. And I say, well, now, if this is a lattice point and this is a lattice point, that is a lattice point, then these two lattice points are closer together. And this has to be the shortest distance. If I can go through something like that, I can use then this distance to make still the shortest distance. Eventually, I have a continuum. So in order to have something with periodicity, or something that is not a continuum, there has to be a shortest distance and nothing shorter. So no rotation more than 6-fold is possible with a lattice. And here's the 6-fold. That's fine. Nothing new is created. The 4-fold, nothing new is created. The 5-fold, it's bigger than 60 degrees, 72 degrees, and you have that here. But now, if this is a lattice point also, you go 72 degrees to here, and you have something shorter. So 5-fold is not okay. And so that's very, very simple and very obvious. And if you have something periodic, that can't happen. So when a law is found wanting, and there's a wonderful book by Thomas Kuhn about structure of scientific revolutions, sometimes it's difficult to distinguish between a law of nature that brooks no exceptions and a plausible principle that works extremely well and has become accepted as a law. First and second law of thermodynamics. Albert Einstein himself said, will never be overthrown, and he put in skeptic's note, because he was one of those guys that overthrew much, but he wasn't going to overthrow, thermodynamics would never be overthrown, but he overthrew Newton's law of motion. That didn't destroy it. Newton's law of motion does not deal with relativity and quantum effects, but it has a large range of where it's valid. So even though we know that it isn't universally valid, we can say there is a range of properties, and we know exactly what they are. It's larger than a few atoms, and slower than some fraction of the velocity of light. So they remain useful and accurate for many everyday problems. The crystallographic laws, based on lattices and periodic arrangements of atoms, forbid 5-fold symmetry, but they remain useful and accurate for almost all crystals. You know immediately whether you have a crystal that is part that has a lattice, and you know that the laws of crystallography must obey. So this wasn't really a very strong revolution, but this is what we published. Immediate worldwide attention, but there was noisy oppositions. People didn't like the experiment. The experiment was very clearly done. But why were they so angry? I've never understood that. There is what was in the newspapers, cold water on icosahedral symmetry, puzzling crystals plunge scientists into uncertainty. That was really wonderful. Linus Pauling was most angry at me because I should have known better. And it was, but this is what came 30 years later, and that because by the time Linus Pauling was making his arguments, there was so much confirmation, so many people, there were 300 papers, so many people had found them, all kinds of new systems had explanations for them. So it was a wonderful thing. The guy here on the left, that's Dan Shechtman when he was a young man. And these are, this is Denis Gracias, who spent a postdoc with De Fontaine here, and that's me. But here Dan Shechtman is explaining to us all the stuff that we already knew. Amazingly enough, there were Moorish tilings with fivefold symmetry. From 1323, the Christians didn't discover it until the 20th century. That's a tiling that's sold commercially. It's a Penrose tiling with fivefold symmetry. Now, what I want to show you is, and this is what's so important in the chemistry of it, when you have quasi-periodicity, the same structures keep coming up. So if there is some structure that is very low in energy, but it can't be packed periodically, you wind up with a quasi-crystal. But it's, and I often say that it's awful to have periodicity. I mean, I know it exists most of the time and it's real, but just think of it, if a tetrahedron is the best way of packing atoms together, in order to make either HCP or FCC, you have to, for every tetrahedron, you have to add an octahedron. And that's not a good thing to do, but you want to pay that penalty in order to have periodicity. You can make an icosahedron, which is 20 slightly distorted tetrahedron, and but then you have to worry about packing them because it has a fivefold axis. So, and the importance of coming up with a structure, quasi-periodic structure, is that nature likes, in complicated multi-atoms, multi-species systems, we've made one binary quasi-crystal, but most of the quasi-crystals are 3, 4, 5 components, and then they're the stable phase, because that way of packing that is not so expensive. So let me see. Okay, this is Abe Awe, René Just Awe. This is from his book. This is where he showed, early on people had said, well, the atoms that make up a crystal must be little miniature crystals, all the same shape. And what he then said is, I'm going to pack a bunch of cubes and look at all the different structures I can make, by just having unit cells packed this way. And as a result of that, we have this funny situation where of the Platonic solids, which were the basic solids, the tetrahedron, the octahedron, the cube, they can be crystals, but these could not be, the dodecahedron and the icosahedron. And but that was accepted, except now it's joined the things. These are some possible crystal forms, and these two are impossible crystal forms. And there is a quasi-crystal, quite possible. Aui's suggestion led to wonderful mathematics. The 19th century, they created catalogs, and a catalog of a mathematician is a complete list. And you've probably in high school gone through showing that there are 5 regular solids, because you go through triangles, squares, and pentagons, and with hexagons you can't make a solid, so there are 3 ways of making solids with triangular faces, 1 way with square faces, and 1 way with pentagonal face. That's all the regular solids there ever can be. And so, but this is a large catalog. The Bible of Crystallography, if you've ever seen it, it's a big blue book, 854 large pages. Everything is in there, but everything is based on this idea of periodicity. That's more or less what I said. This is the old assumption, and this became the defining axiom of all crystals, and it excludes quasi-crystals. And here is the crystallographic restriction. That theorem is correct, but the quasi-crystals have no lattice. Now, one of the amazing things that all of us know is that Aui's assumption of identical units, which required a rational chemistry, because every unit had a finite number of atoms, was false, because we had solid solutions, we have defects. The thing that saved Aui and saved crystallography is that the lattice remained. So here is a very defective rectangular lattice from Seattle. I don't know whether you can see it, but these are streets and avenues, and there is a crazy border where the water comes on both sides, and there are places where there are hills and it goes far, but you can find the lattice. So all of the defective crystals, which really were not ideally periodic, fit into crystallography because you could find the lattice. And so therefore there was no extension. But you can't do that with the icosahedral quasi-crystal. There was no way of doing it. By the way, there were quasi-crystals as early as 1920. The incommensurately modulated structures are never periodic. You have but we considered them to be crystals. Basically, we forgot about the modulation. We considered them to be crystals, and then we said, well, then it is distorted by an incommensurate modulation. But that made it totally aperiodic. But it had a symmetry if you ignored the modulation, and a lattice if you ignored the modulation. So there was no revolution at this. With the icosahedral one, the revolution occurred. So what is there in quasiperiodicity? It's a superposition of more independent periodicities than there are dimensions. And this isn't at all uncommon. When you listen to a tone that is beating slightly off, you're beating two different frequencies together. If they are incommensurate with each other, then it's quasi-periodic. It will never repeat. But it doesn't sound any different than one in which there is something. And so because there are more independent dimensions, you can always put something quasi-periodic into a higher dimension and then slice this higher dimension on an irrational plane to get the quasi-periodicity. And this is the easiest way to look at it. Quasi-periodicity is aperiodic, but approximate repetitions on all size scales occur because you're slicing something which is periodic in a higher dimension. And I'll demonstrate this a little bit. Higher symmetries are allowed, so you go to 6 dimensions. And, for years I was saying, I'm doing 6-dimensional crystallography, and people looked at me like I was crazy. But it was easy to do the icosahedral one. And quasi-periodicity opposes fewer constraints than periodicity. Therefore, you have the possibility of lower energy. And in fact, Cahn, who is a mathematician in Texas, has for years said, why do we have periodic things? There is a higher infinity of of interactions which will give quasi-periodicity. It has to be a lower infinity of interactions that give you. So if you randomly reach in, you almost always to a box of interaction parameters, you almost always get quasi-periodic. You have 0 probability of getting an interaction and he sort of says, what is it? Is it that you make the periodic lattice because of kinetics, that layers repeat, and then it has no chance of transforming to the truly lower energy? But here is an example of quasi-periodicity in, I'm taking cosine x plus this cosine the square root of 2x. Now, square root of 2 is totally irrational. And you see here what sort of thing it goes. The only place where it is 2 is when x equals 0. Thereafter, there are peaks, but they never again will reach 2. And so here I did it between 0 and 100 for x, and there I did it from 1,000,000 to 1,000,000 plus 100x. So that's the red curve. And I just picked that at random, but it always works. I find the highest peak in this one. I didn't pay much attention to that one. I find the highest peak here and the highest peak here. And here they're brought almost into coincidence just to show how they are. And then when you bring them into exact coincidence, it's smaller than the thickness of the line. And this goes out to infinity in all directions. So with quasi-periodicity, things repeat. And so, but the translation from this to 1,000,000 that produces this. If I try to go to 2,000,000 and find this peak, it won't be quite as high. And if I go to 3,000,000, so the translations are not a periodic set. They are peculiar, and what they are the line on an xy plane that starts from the origin and goes up with a slope of the square root of 2. Every once in a while it gets very close to a lattice point, and that's a translation. And but it's a certain distance away from that translation. Twice as far would be twice as far away, so it won't be as good a fit. But it'll come, and they'll come in aperiodic ways. That's quasi-periodicity. But now that you've had this lesson, this is a practical example. This is the stairmason's dilemma. The owner says, "I want to have stair, and these are chords that I don't want the stair to be above that chord." Well, if the slope is rational, like 1 and 1, here, you have one step, you go up a step, you just go up a step, up a step, up a step. It's beautifully periodic. If slope is 2/3, you do 2 you do one step and then another step and then another step, but it's periodic. Sometimes there are two steps, sometimes there's one step, but it's perfectly periodic. If I now pick some irrational step, there'll be a step here, and then there'll come a step there. I can't quite see it from here, but it will be between 2 and 3. You'll go 2 or 3, and then you go up a step, and then you go 2 or 3, and so on. It will look periodic, but it will really be quasi-periodic if these are irrational. So that's how you go from 2 dimensions where everything is periodic, and then you slice it and create that. So here is a cube, bunch of cubes, and you take an irrational plane, and you have a 2-dimensional, this is now 2-dimensional quasi-periodic tiling. It will never repeat, but you know exactly what it is. It came out of 3 dimensions into 2. And okay. And that's indeed the lesson, the repetitions. Now, for the next topic in this thing, I wanted to tell you about a semantic problem. We call glasses amorphous, and yet Professor Joke, who won the Nobel Prize in Chemistry in my time, had already shown that must be on a different one. Well, Professor Joke had taken on a glycerin glass, maybe it's on the next one, yeah, glycerin glass in the 20s, and measured its entropy, and it had a very low entropy. And then we have the Kautzmann paradox and Turnbull's work, and then there's a wonderful guy by the name of Zugukov, who's now in Sweden, who has decided he's going to do a pair interaction where he has a well so that you form nice tetrahedra, but he's going to make the octahedron very expensive by having a high energy at the distances of the octahedron. And he's been trying to make a development which is a model of something where the ground state is likely to be glassy, to be isotropic. And there's a lot of controversy. This has been going on for 30 years. But Mendeleev, who's at Minnesota, has done an MD simulation on aluminum. And he finds that there is a metastable phase which is isotropic. And it coexists with the liquid. And there's a melting point of it. When you heat it, the interface between the liquid and this glassy phase moves up, and if you cool it, it moves down. It isn't that the glass melts by uniformly melting or forms by crystallizing. He unfortunately used a very poor model for his thing, but the fact that this exists is fascinating, that you can have an isotropic solid phase different from the liquid. And so this is my most recent work, Structure and Thermal Evolution of Metallic Glass that Grows from the Melt Like a Crystal. We found this as a failure when we were trying to make quasi-crystals in '88. And here's a picture of it. Here is primary glass primary glass, primary glass, primary glass, and surrounding each glass particle is a eutectic of glass and aluminum. This is an aluminum iron silicon. So for metallurgists, this is no problem. We know this is the primary phase. That came first, and then other stuff crystallized. So this glass grew from the melt. More than that, this glass rejected aluminum into the melt, and on higher resolution you can see a thin band that is mostly aluminum before the eutectic sets in. So there's coexistence with partitioning, and that's a hallmark in multi-component system of a first-order transition. So this glass formed from the melt by a first-order transition. Here are transverse sections from the wheeled side to here. Here's a failure where we can see, well, it was a bubble here, so it didn't cool quite so well. So we can see that if we don't cool it well enough, it forms two phases. And this is, oh, by the way, this is a different composition from that. This was a composition where we found it. We then found what the composition of this is, and we made 100% glass. And here is a diffraction pattern. It looks very glassy. But it's different from the liquid. It is not a frozen liquid. So what is it? Well, it has incredible order. We went to argon, and we went out to 18 angstroms. And we have compared with crystals and with an icosahedral phase in this system. It has a structure of its own. And this has been known to the mathematician. Here is a pinwheel tiling, which is more or less isotropic. Every orientation exists in this tiling. It's made by taking a triangle, subdividing it into 5 triangles, then subdividing each of these into 5 more triangles, and eventually you make an isotropic mess. Here is there are now computer programs for making Penrose tilings, and here's one which I did with 19 full tilings, and that's the diffraction pattern. Now, to me, that looks like a glassy diffraction pattern, except each of these are Bragg peaks. So if I gone to more than 19, and this is what the tiling looks like, and here is the tiling again, and this is what the atoms might look like. So it is possible to create something isotropic that's highly structured. And it's structured in this case in the same way as quasi-crystals are, except now instead of being just icosahedral symmetry, it has all the symmetry. And so we may be on the verge of another kind of structure that is like quasi-crystalline, but it is isotropic, and it has different stability. These glasses, because they're formed from a first-order transitions, have thermodynamics much more like crystals, whereas if you cool a glass and by freezing a liquid, it always has a higher energy than the liquid. It never becomes stable. So let me go quickly now. How are we doing in time? No, I have no more time. All right. I was going to do some things about kinetics, but it's. Let me just do it very quickly. This is one of my favorite slides. So there's no need to put an engine into a thing if you listen to the thermodynamicists who use things like this, that if you have entropy production, there are fluxes and forces, and the fluxes, of course, are kinetic. So here is a car which doesn't have an engine, but it has a gas tank and it has a fuel pump attached to the wheel. So if you push it, entropy is being created. So it doesn't have to be, it should just go by itself, because once you start it moving, you're constantly creating entropy to keep it going. And so that is something. Now, here is an old slide of mine on discontinuous coarsening. I guess I want to see that one. This is the fine structure here, is a very fine lamellar structure, which we made by directional cooling. And we were going to make a beautiful lamellar structure which had wonderful mechanical properties, but unfortunately it discontinuously coarsened. Now what's happening here is that it's not moving in this direction very much. It's running in this direction, and it's not going out in this direction. Now, if I convert this to that, I have the same free energy change than if I convert this to that. So there should be no difference in free energy change no matter where the boundary moves. But if you now look a little bit further, you say, well, here these guys are pulling on this boundary, and here the guys are parallel to the boundary. They're not pulling. So do we go by free energy, or do we go by the mechanics? And the answer is we go by the mechanics. So here is, assuming the lamellar interfaces remain straight, there's this angle phi between a boundary and so it's moving up in this direction, being pulled by these. So the boundary has 2 cosine phi over lambda, and the force from the interface is this. That's also cosine. So we have a cosine squared from here. Whereas if we just, that cosine squared would not be there. It would just be 2 gamma over lambda if we simply dissolved this stuff and turned it into something with no lamella. So the general driving force is isotropic, but when we look at the pulling of it. Now the next thing is something really strange. If I let the lamellar shape change, bend around, because this is not really the equilibrium angle, I'm dissipating some of the available free energy. But now the lamella are pulling straight up. They're still at the same spacing. And now I have a greater driving force. Even though I've dissipated some of the available free energy in this reaction, the driving force has increased. And that's what the situation is. Looking at just the free energy driving it, you get this. If the boundaries don't change, you get cosine squared. And here you get cosine, which is faster, even though some of the energy has dissipated. So these rules are, I don't know what the general rule is. I hate to say it's going to have to be done for each case, but I hope one of you will solve that. Okay, I think with that I'll go to the end and simply say fallacies can become false paradigms in our field. Classes are amorphous, kinetics driven by thermo. We can detect them as fallacies, but what will be the new safe paradigms is usually fast from clear. And I want to thank you all for coming.
Thank you, John. Thank you. So we're kind of out of time. Maybe if there's one short question for John, and because we do have something we want to present to him as a token of thanks. Is there any short question or comment? No? Okay, so maybe what we'll do is we're going to make a little presentation to John as a token of thanks, and afterwards we'll stay here, and anybody who would like to talk to John is welcome to do that. So maybe I can present John with a little token of our appreciation.
Thank you.
So, first of all, as part of the Dow lecture, there's a little bit of appreciation in the form of some money. Now, you told us as well that you didn't want a plaque.
Yeah.
But we felt that we should give you something to remember us by. So this is a piece of crystal that I don't know if you can see that, but it has your name engraved on it. And
wow.
Yeah. And so. So anyway, with that, I just want to thank you one more time, John, and for a wonderful lecture.
On the plane tomorrow, I will be pulled aside. Because this is lead glass. Wow, is that
Is this
heavy?
the glass, or is this new phase of matter that you found?
I'm sure that's an old-fashioned kind of glass.
Yes. Okay. Okay. Thanks again, John.
Okay.